that Phantom of the Opera wasn't your favorite movie. Okay, musical movie. Play.
Was that a W? I'm gonna find it. I'm gonna send it to you guys. It was funny. At home. I hate you. She's like this at home.
Okay, guys. Good afternoon. We'll get started here in a minute. Any questions while we have a minute? I was rolling in the cart, using this cart. When I roll it in, I feel. You ever go to the Japanese steakhouse and they roll the cart up to the table? I feel like I'm rolling in the cart. We're gonna make some. What are you gonna whip up?
Rice.
Big thing of rice.
Rice.
Questions? The question up here? The Alkene puzzle, pink sheet, number 17. We've not covered that reaction, number 17 on the puzzle. HBr peroxides. Yeah. And it's pretty much time to get started. HBr peroxides. Whenever you put the peroxides in the reaction, you get the reverse regiochemistry. That gives the anti-Makarnikov product. Okay? So the opposite. Instead of H here, Br there, you're going to get Br here, H there. Okay? In terms of mechanism, that's a radical reaction. We may or may not cover it. I'll eventually would have said something about it at some point. But when you see the peroxides and HBr, reverse the regiochemistry. The radical makes it go opposite. We can look at the mechanism maybe at some point. But that reaction is in your textbook. Anti-Makarnikov. Okay, time to get started. A couple of things. The bromination report, the transtylbene bromination that's due in here on Tuesday. Okay. With the official projections today. Your polarimetry worksheet is due next week in lab, except for the Friday group, which you will not have lab. That will be turned in here, I reckon, Thursday. Next week in lab, we're not really doing we're not doing a true lab. We will talk more about what we're doing in the lab when you come there. What's written on the outline is to go over the SciFinder database, and we may also go over some library stuff, but we may do a little bit something else also. I'll see you in lab on Monday, yeah. And you'll turn in your polarimetry worksheet in lab. Transtylbene report due here on Tuesday in class. Okay, quizzes turn back at the end of class today. There's several 10s on the quizzes, good job. Fortunately, there was lots of 1s, 2s, and 3s. Lots of, in terms of the mechanism, predict the products, a lot of just stuff that was being made up on the spot. I'm not sure what it was. Mechanisms are highly important. You need to figure out how to open the textbook, learn the mechanisms, review your notes, learn the mechanisms, rewatch the videos, learn the mechanisms. My office is is located on the 3rd floor. The office number is on the syllabus. Some of you come by, but the majority of you I've never seen outside of lecture and lab. Okay. Yellow sheet is our outline. Enantiomers of 2 butanol, we did that. We assigned one as R and S, one of them was also D and L, that's based on the specific rotation. Enantiomers will rotate plain polarized light one way or the other. We said that one enantiomer was plus 13.5 and one was negative 13.5 degrees. All right, that's just the experimental outcome. That is, for 2-butanol, if we have all 100% S, our rotation would be what? Was that positive or negative? Positive. S was positive, okay, positive 13.5. If we had 100% R, it would be a negative 13.5. What if you have a mixture? First off, the easiest is, what if you have a 50-50 mixture of the 2 enantiomers? It's actually 0. 50-50 mixture is called what? A racemic mixture, sometimes called a racemate. A racemic mixture, 50-50, is not optically active. That means it does not rotate PP light. Why? Ultimately, it's because half the molecules rotated one way, but the other half rotated back just the opposite, and you end up with nothing, a net of 0. So there's no net rotation. They cancel each other out. So 50-50 is easy. But what if it's like 75-25? Something like that. We need to look at that. And that is on more on optical activity. Before we do that, we can maybe look at the top with the 3 compounds drawn up there. Document camera. I'll also probably refer to something in the white. You can look at that there. Identify chiral carbons in the compounds below. Okay? Do you have any chiral carbons here? No. Now, hopefully everybody's in here has already done this because you were prepared for class and you were looking what we're going to be looking at. Okay, boom. The answer is no. There's no chiral carbon here. Is that chiral? No, it does not have 4 different things attached. It's got a chlorine, it's got an H. How do you deal with this ring? If you go this way, you get the same exact thing. Okay? No difference. These roads are no different. Not chiral. How about here? Anything chiral here?
Yes.
You go that way, this way you get double bond, that way you don't. Is that chiral?
Yes.
No. The carbon doesn't have 4 different things attached. It's only got 3 different. It's got a chlorine. There's no H there, is there? Okay. What's the geometry of that carbon? Trigonal. Planar. A planar carbon is not chiral. A planar carbon has a plane of symmetry. That's the plane. Okay? Now indeed, that plane you can slice right through like a piece of bread as long as it's both same on both sides. You can't slice right through my hand, where you'll get a top of a hand on one of your slices and a palm on the other. But a piece of bread is not like that, as long as you don't have like some sesame seeds on top and then on the bottom. Okay? And an atom is not like that. If you have a planar atom or a group of atoms, you slice right through them, the top half is the same as the bottom half. A planar carbon is not chiral. How do you get a chiral carbon? It has to have 4 different things attached. It has to be tetrahedral. Okay? Neither one of these have planar carbons. Neither one of these compounds are chiral. They both have planes of symmetry. I mean, if you really drew in this H here, this chlorine is really forward, and the H is really back, but the H is really right behind that chlorine. Okay? It's really right on top of it. And then you can draw right through there, chlorine slicing through that H right behind it. This is the same. This side's the same as that. Okay? Same thing here. See, that's all planar. Now, while this is not planar, you can consider it as it is. Because you do have chair and flexibility over here, but this type of thing, you consider it flat. We can talk more about that. But basically, there's no chiral carbon here. If there's no chiral carbon, 99% of the time, the compound's not going to be chiral. There's a couple of exceptions where you can have a chiral molecule but have no chiral carbon. But that's not it. No chiral carbon. Do we have a chiral carbon here?
Yes.
Yeah, here we do, right there. Because there is an H that is tetrahedral. And so you have 4 different things. Drawing the H, if we make that bold, we can draw in the H dashed. And then that carbon has a chlorine and H. This way and this way is not the same. This way you come through the double bond. This way you do not. Now if we put a double bond there, then it's no longer chiral. But because of that, we can no longer then slice right through this. Again, that H is right behind that chlorine. Because you've got a double bond on one side, but there's no, you need to be mirroring with a double bond over there. So there is no plane of symmetry now. Because there's no plane of symmetry, what do we know about the mirror image? Not the same thing. It's different. That's the definition of chirality. Mirror image is different. So we call it a chiral carbon, but also the molecule as a whole is chiral. Okay, so there's just a few examples. We can do more. There's miscellaneous ones in the handout. On the front it says, how many chiral carbons in these drugs. You need to find them, etc. We haven't done that one yet. Let's look over here. Here's just some more drugs. I give you examples. I ask you if it's RS. So you just do examples. Let's look at this one over here. That's compound levofloxacin, Levaquin. Anybody heard of Levaquin? Antibiotic? Yeah? Here's Levaquin. Okay? Carboxylic acid, ketone, amines. Is RS. Well, what are we looking at? Where do we need to look at? RS, chiral carbon. Where's the chiral carbon? Now in this case, we can see it because the structure shows it dashed in bold, which you need to determine RS. Some structures are shown generically, and you just have to find out that, hey, that's the chiral carbon, and I have 2 ways to show it. You can show the methyl forward, or you can show it back. Here it's forward. Is that RS? What's 1 here? N, carbon, or carbon? N. Carbon all H's or carbon with an oxygen? Then carbon with H's? That'd be 4, right? And 4 is in the back, so that's good. So with 4 in the back, what is it? It's S. It's counterclockwise. Okay, it's S. Now it's a hemihydrate, hemi meaning half. Every mole of the drug has a half a mole of water with it in the crystal structure or when it's given. Okay, is it D or L?
Do you not determine it because you don't know which one is positive?
D or L has nothing to do with S or R. Sometimes chemists like to use information in the name. What's the name of this drug?
So it's probably N.
Levofloxacin. Why did they call it levofloxacin? Because it's probably levorotatory. Indeed it is. It's L. Remember, names can sometimes give you information. But it has nothing to do with RS. There's other ones there. Actually, levofloxacin is given as 1 enantiomer. It used to be given as racemic mixture. Both enantiomers, 50-50, right, as a racemate. I don't know if that was called ofloxacin or something. And then, of course, when that patent ran out, they didn't got a new patent on the just the one enantiomer, so they can keep charging lots of money. Let's look more on optical activity. Okay, 50-50 mixture gives no net rotation. We've already said that. This is called a racemic mixture or racemic. What if we have something that's not 50-50 or not 100% zero? First off, there's terminology. We describe mixtures using the term enantiomeric excess, EE. Okay? This is when you have a mixture, but it's not racemic, not 50-50. The EE is the excess of one enantiomer that exists beyond racemic. First of all, we're going to do a little bit of math here, and if you want formulas, look in the textbook. I'm not going to give you a formula. I'm going to explain it to you. What I mean, the EE is the excess of one enantiomer that exists beyond racemic. For example, if I said a mixture is 80% S enantiomer and 20% R enantiomer, what is the EE of this mixture?
60%.
It's what, T?
60%.
Who's that?
60%.
60%. Yes. It's a 60% EE. It's really the difference between your two percentages. Now, if you try to think too much, you'll say, well, that's like 400% more than this and all that. Okay, no, it's just the difference. What do I mean by it's the excess beyond racemic? Look at what racemic is. If you turned this 80, if you took some of that and canceled this, you take 20% of this to cancel 20% of that. So turn this here instead into 20% and 60%. Okay? Now 20 cancels 20. This is racemic. 20 and 20 cancels. What are you left with? 60%. That's the EE. This is the amount beyond racemic. That's what I mean by this. It really comes from what it does with the optical activity. 20 cancels 20, and you're left with 60% rotation. That's the EE. And so you would say, hey, this is a 60% EE. Now, when you say something 60% EE, you could be asked, well, what's the ratio of the components? Is it 60-40? No, it's 80-20. We'll do examples. But that's the EE. There's one up here on the text. A mixture that has an EE of 10% R. Well, that's going backwards. If it has an EE of 10%, what's the actual composition? It's 55-45. If you go the other way, you can turn, okay, how much of this needs to cancel that? 45 cancels 45. What's left over here? 10. 10% is left. That's the EE. What's left beyond racemic is your EE. So you call a 55-45 mixture, you say, hey, that's 10% EE. But again, it's really just the difference between the two numbers. We'll go both ways on this. Let's see what's next up here. What is the ratio of D to L? Instead of calling it R to S, I'm calling it D to L. But when you have enantiomers, isn't one D and one L in terms of how they rotate light? So we can use that terminology. What's the ratio in a mixture that has an EE of 60% D? Think about it for a minute. If the E is 60%, what's the percentage of each? 80-20, right?
Yeah.
80% and 20%. How do I know that's 60? Because if 20 cancels 20, what are you left with? 60, which is So it's 80-20. What's the ratio? It's 80-20 or what? 8-2 or 4-1? I mean, you can take it down to 4-1. Let's go the other way, I think, here. What's the E of a sample that is 70-30 DL? That is 70% D and 30% L. 40. That's easy. 40% EE. Because 30% of this cancels 30% of that, what are you left with? 40% of which one, though? D. You need to kind of say which one. 40% enantiomeric excess of D. What if it's 50-50?
0.
Well, if that cancels that, what are you left with? 0. 50-50 is no EE. It's 0. It's called receiving. So that's EE. It's just terminology that's used to quote it, but you have to figure out, okay, what are we really being told here in terms of what's really the ratio of the two? Determining rotation. Okay, you were determining rotation in lab this week. Some of you have done it, some not. The rotation of the plane polarized light. If it's 50-50, it's 0 rotation, right? If it's 100-0, well, it's whatever the number that's known to be accurate, either like plus 13.5 or negative 13.5. Okay, something that had to be determined. That becomes a physical standard for the enantiomers. But what if it's a mixture beyond something like this? Only the excess beyond racemic rotates. The only thing that rotates is your enantiomeric excess. Because remember, the remainder cancels each other out. And it cancels each other out in terms of rotation. Percent rotation is the same as the percent EE. Thus, a mixture with a ratio of 8-2 or 4-1. Let's keep it 8-2 so it's kind of like out of 10. 80-20. That means it has an EE of 60%. It'll rotate light 60% of max. Now, if this was 8-2 of the 2-butanol, then we know max was what? Negative 13.5. Plus or minus 13.5 for 2-butanol. So if you have a mixture of 80-20 R to S, what will be the rotation of this mixture? It won't be 13.5, it'll be what?
2.7.
How'd you get that? What was the math?
20% of 13.5.
What percent?
20%.
Why 20%? Why 20%?
You don't know that.
He did A instead of. He just did A. He goes in.
No, it's
He did that one.
it's American.
Oh, I'm sorry. There's two different ones up here?
Yeah. Yes.
Okay. Yeah, up there it says 82. Okay, here, okay. Right, let's do this one down here, which is actually 2-butanol. Okay. Yeah. That's 60% up there. It's the same idea, it's just a specific problem. 2-butanol, we know it's plus or minus 13.5. What would be the optical activity of a 60-40 mixture? Well, what's the EE here?
20%.
20% EE. How do you get 20%? Because if you turn the 60 into 40-20, and then the other one's 40, the 40 cancels 40, leaving you with just 20. That's 20% EE. But this is also the rotation, because rotation of 40 one way is canceled by rotation of 40 the other way. So that gets washed out, and you only get rotation for what's remaining. So you only get rotation for the 20. You only get rotation for the EE. And you're only going to get rotation 20% of max. Max was 13.5. What's 20% of that?
2.7, I think.
2.7?
Yeah, I'm pretty sure.
Good. We got to look at a sign, because what's the major one here? R. 20% EE of R. Don't forget which one you're talking about. R is the major one, the one that's in excess. R is, was it negative 13.5? So this should be negative 2.7. So that mixture should give a specific rotation of negative 2.7, which is 20% of max. Again, because the 240s cancel each other out in terms of the rotation. Now we can go backwards here, and from this type of number we can determine the ratio. Let's try that here. What is the EE of a sample of 2-butanol if the rotation that's measured is negative 10.13? How do you want to do this? Go ahead and do it if you know how to do it. You're just going the other way. You're just working backwards from how we got to that. Somebody do it and tell me what it is. It should be a whole number, because that's probably why. Is it 75? What does it say here? What is the EE? You're saying the EE is 75?
No, 75% R.
75% R?
Yes.
I reckon that means it's 25% S. But the question is, what's the EE? So what's the EE? EE equals 50% R.
Don't you use EE
What do you
in
use
calculation?
percentage?
So it's 75%.
It's 75% EE.
Not all R.
We need to go back. This is 50% EE. But that ain't the answer. Because that ain't the answer. How do we do this?
You have to divide negative 10.13 times divided by 0.2. You divide it by 13.5 to determine your EE of R.
We need to know this is what percent of max. That's what we need to know. What is max? Okay. Is that 75% of max? That's what we need to know. That's 75% of max. You get that by dividing it by max and multiplying by 100. Now that we know it's 75% of max, what is our EE? Second line, number 3. The percent rotation of max is the same as the EE. 75% EE. See, the EE is what rotates. Since it's 75% EE, what's the ratio? Well, first off, that answers it, because we were only asked for this. But what is the ratio? 88.5 and 12.5. Is that the ratio?
87.
87.5.
7 to 1.
Is that the ratio? That's a 12, right?
Yeah.
There's your ratio right there. Let's go backwards and make sure. Because if this is the ratio, what's the EE?
75.
You need how much of this cancels that?
12.5.
12.5 cancels that. What are you left with here?
75.
75, which is what you're left. That's the excess. It's 75% EE excess. See, and that's where it rotates. Because the 12.5 cancels the 12.5. That's the only thing left to rotate. And so you get 75% of max. Well, 10.13 is 75% of max. It only rotates this much because that is canceling some of this out. Okay, I went through it without using formulas. I could put up formulas and say, put in the numbers, here's your answer. But I hope the way I went through it helps you understand it a little bit. Look in the textbook. If you want a formula, it'll be nice and clean. You just put your numbers in. Any questions about this? Did how I kind of explain it make any sense? Is it now usable?
Yeah.
Or you just want to plug numbers?
Reasoning.
Question?
So does this sign indicate whether it's
We might not have done that. Did we indicate which one? Well, it was negative here. Was R negative 13.5? Yeah. It's more to the negative, so it should be more towards the R. If it moves positive, that means it's going to be more towards the S. So you would only get positive if there's excess of S. You get negative if it's excess of R. Yeah. So we do need to clarify this. So it's R to S here. R is negative, correct? R is lever rotatory?
Yeah.
Question? Well, we determined the EE was 75% excess.
Yeah.
Basically, this is the difference between your two. How do you show a difference between this? You show this right here. Is the difference between these 75? There's some formula that would give you this. I don't know what it would be. 100 minus. Yeah. I just said, okay, I need to show two numbers where the difference is 75. And I kind of figured it in my head.
So you don't know, like, you don't know the process that you
If you want a formula, it should be in the book. Do you understand, though, if you want a difference between 75?
Yeah, I understand, like, what you're doing. It's just, I didn't know, like, how you just, like, oh, okay, these are the numbers.
Well, I use this example every semester, but it's you need two numbers where the difference is 75.
And then they have to add up to 100.
Add up to 100, yeah.
But
Yeah.
there's a formula that you can use that'll give you how to get from 75% to 87.5.
I think there's probably one out there. But this is all what you're doing in lab this week because you determined a rotation from your experiment. From the rotation, you can then say, okay, what's my ratio of enantiomers? Now you were given like what, plus or minus 11.0? That was kind of like the literature? Okay. And the safe one is lever rotatory, so it'd be you would hope to get negative 11.0 after you standardize it. See, the standardization is basically turning your denominator into 1. And you do that by dividing by concentration and half length. Okay? If your standard is not 11, negative 11, well, if it's negative 5, that means it's not 100% that one enantiomer. Something is causing it to shift the other way.
But Dr. Stevens, I thought L and D were how much it would take to play polarized light.
Right.
Didn't you say it was like R and S a moment ago?
But on Tuesday, we said for 2-butanol, or it can also be called L. Is that right? Yeah. So at that point, we can use, I mean, you can call it L-butanol, L2-butanol, or you can call it R2-butanol. That's the same compound. Once you know how it rotates. But one of those has to come from experiment. The other just comes from how it's on the board. Okay, we really need to hit Fisher projections. That math, I think, check out the textbook, see what type of questions come up. You're doing it in lab. Ultimately, it's pretty straightforward. You just have to let it kind of sink in and just think about it. Fisher projections. Spelled with a C. This was Emil Fisher, chemist, back in the 1800s, etc. Show one bromo, one chloroethane in a Fisher projection. Next, show the Enantiomer in a Fisher projection. Okay. Here's S. Show S and then show R. I think I just added these. I assume this is S since it's on this side. Let's make sure. Is this S?
I think it's R.
That's R. You think it's R?
Yeah.
I think
Counterclockwise, and then since the bromo's in the back, it has to flip it.
Yeah, but see, where's the H?
In the
Is the H forward or back? It's neither. When the H is not forward or back, you have to look at it differently. If it's back, you don't have to do anything. If it's forward, you do it and just reverse it. If it's in the plane like this, you have to look at it differently. And that's the power of the Fisher projection. You need to look at this differently. Let's draw this in a Fisher projection, as it shows up here. A Fisher projection is where you draw just crosshairs, and the chiral carbon is at the crosshair. If you have multiple chiral carbons, you'll have multiple crosshairs here. Whenever you see the crosshair, it has built-in meaning. The stuff on the side is coming out towards you. Like cat whiskers or a bow tie. The stuff up and down is going away from you. Okay? So that's that. Whenever you see crosshairs, the stuff on the side is what? Coming out, trying to hug you, right? Stuff top and bottom, they're going back. That's implied in the crosshairs, and this is called a Fisher projection. Now, in terms of a model, you actually see here, none of these bonds are in the plane of the board. 2 bonds are going out, 2 bonds are going back. Here's a tetrahedral. Let's put a red back on there. It's called H gray, yeah. I think chlorine we were calling green. I think bromine was red, wasn't it? Yeah. It really doesn't matter. Today we're going to call chlorine green. All right? And thus, is that compound there? Yes. Yeah. Methyl straight up, chlorine forward, H in the plane. It's kind of like this, the board here. The bromine going back behind the board. Okay. Now here, I've got a plane, and this and that are in the plane. That there is where this is turned. I don't have things drawn on it, but I can show this. Is it like that? Is that like that? No, it's actually like this, right?
Yes.
That is, the things on the side are coming out towards you. Top and bottom are going back. See, that's how it's supposed to be. And now, there's nothing actually in the plane. 2 forward, 2 back. if I want a plane, I can turn it like this, and now I have the plane in the green forward, the red back. But there's actually nothing in the plane here. And that's the fissure. Now let's take it back to here. Green forward. There it is on the board. How do I want to draw this? Let me look at it. Something like that. I'm going to turn it as if I'm looking at it like that. I'm going to turn it like this. Now the black's going back and the gray's going back. That is, the things that are going up and down are going away from me. And the things that are coming towards this side and that side are coming towards me. Isn't that now like a fissure? Really, I want to draw what I see right there. We just turn just a little bit. What do I see here? We're going to do this sort of like Newman's. I'm going to stand over here, look through here. Those are my eyes looking through there. Here's the ground. Later on, we got to keep our feet on the ground. Look through here. We'll do this a couple of times. What do I see going straight up? Nothing. I'm going to draw it straight up. I'll put an ME there. That's a methyl. What's a methyl? CH3. Okay. What do I see going down and kind of away from me? Yeah, see, it's like that. I'm going to do it like that. See that H coming down and going away from me? If you can't see it, you want a better view, say, hey, I want a better view. H going down and away from me. So can I put that there? Isn't that what this means? It's going away from me and down. Down is down. But it's also going away. As I'm looking through here, what's on my right because it's coming towards you? Chlorine. And also, is that chlorine coming towards my little man or going away? That's like this. Coming towards and towards y'all. So it's going to my right as I'm looking through here. That's it. That's just what I see here. It's going towards you, which is my right. It's also coming towards me. See to the right, and it's bold coming towards you. The chlorine's here. Where's the bromine? It's here, because as I look through there, bromine is going behind the board. And so it's on the left. Somewhat like Newman's, except we're not looking down a bond. Right here, we're just looking at a single carbon. Later on, we'll look at two carbons. But that is that. That's the same compound. But now it's in what we call a Fisher projection or crosshair. Now that it's in Fisher, it's much easier to do things with, for example, determine RS. This carbon, it's chiral. What's priority 1? Then 2, then 3. What do we got here? Counterclockwise, how is the H? It's down. What does down mean in a Fisher? Back. So counterclockwise with the low priority group back, it's what? S. Why did somebody said that was originally R? Who said it was R? You said because you. Okay. Problem is the H is not forward or back. The way you did it was not right. The H has to be in forward. You can do it and reverse it. But now we're actually looking at it with the H back, because how am I looking at it? I'm looking at it, and where's the H? It's back. But instead of looking at it and then thinking, okay, well, what am I seeing? I drew what I see. Then I determine. Okay, over here. Is this RS? I'm going to stand over here, look through there. I see something going straight up. What is that? Methyl. What's going straight down towards my feet? This is the ground. What's coming to my left as I'm looking through there? Chlorine, bromine. That's it there. 1, 2, 3. Clockwise, the H is, okay, so that's R. Can you also see that those are mirror images? Look at the two fissures. Do they look like they're mirroring each other? When it's in a fissure projection, you can also see the mirroring better. Well, you can actually tell these are mirroring too because of the way I drew them. Who's first?
With that one, like, what if you have to look at it in a specific way? Because what if your man was placed on another picture?
Well, if I'm over here, how about over here?
Yes.
Methyl up, H down, but they're coming towards me. That H is coming towards me. The thing that's down is going away.
Yeah.
So I need to look at it with the thing going down away. And the things on the sides are coming towards me, right? So if I'm over here, the things on the sides are going away from me. So I want to look at it from over here. You see how the chlorine and the bromine are on the sides?
So you want to look at it in such a way your lowest priority group is down?
No, you want to look at it as a way with things on the side coming towards you, because that's what you're drawing.
Okay.
If the high priority group, see here, things are either forward or back. Because if the H is here, it's back. If it's there, it's forward. And we know what to do if it's forward. You just reverse what you get with the clockwise.
Would it make any difference if the placing your methyl and your hydrogen were switched? Or does that even have to be switched?
You mean in the fissure?
Yeah.
Yes, it would. You would have the enantiomer. Why would you want to switch? The methyl's going up. You gotta know where the ground is. Ground is here. The H is closer to the ground. H is closer to the ground. You can show me what you're thinking about. Okay, let's look at the outline. Compounds with more than one chiral carbon. How many stereoisomers are possible for this compound? First off, how many chiral carbons? 2. Yeah, that's chiral. It's got 4 different things attached in that. 4 different things attached. 2 chiral carbons. So that's step 1 you have to know. So how many stereoisomers? Awesome. Now here I give you a formula. Number of stereoisomers, does it say? Maximum number of stereoisomers? Does it say anywhere? Okay.
Stereoisomers are possible to follow process.
The answer is 2 to the n. Maximum number stereoisomers. 2 to the n. What is n? N equals, it's more than just chiral carbons. Chiral carbon is an example of what it could be. Stereogenic sites. Because we have more than just chiral carbon. What's another type of stereogenic site? An alkene. Alkene. Remember the video? The presence of an alkene can sometimes, not always, but sometimes it can lead to cis and trans, right? It can lead to stereochemistry. We'll see. A lot of people will just say chiral carbons, but it's not. Okay? How many stereogenic sites do we have in this compound? 2. 2 to the 2 equals 4. I think it's 4. 4. That's the maximum number. There could be less if some of them are meso compounds. We we'll explain that when we get to there. For this one, it's indeed 4. Can you draw them? First, as a perspective drawing. The perspective would just be using the dashed and bold. I'll do the first one for you. Let me do it a little bit low here. By the way, we've already done 2 to the 1. What does that equal? 2. When there's just one chiral carbon, you got 2 stereoisomers, the R and the S. 4. First one, I'll probably get rid of this. Let me draw it down here. How do you draw these? Well, just like we drew like the 2-butanol. Let's draw the OH bolded. That's tetrahedral. 2 in the plane, 1 forward, 1 back. And let's draw the chlorine. How do you want to draw the chlorine? Bold. Here's 1. Now let's draw this bolded. And to be different, we're going to draw this dashed. Here's 2. I might do this some other way. How about dashed here and dashed here? And then the 4th is going to be what? Dashed here and what? Bolded here? I'm thinking we can still see with this projection up here like this. Well, there's 4. Are those 4 different? Are they really all different? Before we go any further, let's do R and S for each here. Just do R and S for all your sites. Here first, R and S. What is the orientation, the configuration about this carbon? 1, carbon with chlorine or carbon with just H's? There's an H here, it's going back, so that's good. Low priority group is back, so what is this? R. All right, that's R. Let's get rid of those. How about this guy? Chlorine with 1. Carbon with O or carbon with H's? O. Carbon with H is 3. Where's the H here? Back? So that's good. 1, 2, 3. H is back, so this is R. Okay, how about the others? What is this one? R. What is this one? S. 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 R. As long as we don't change the backbone, it should be the... See, the backbone is zig, zig, zig. And if that's R, if I switch to that should be S. You can check yourself. We got RR, RS, SS, and SR. What's the... All of these are stereoisomers because they have the same connectivity. Everybody agree they have the same connectivity? An OH connected to the second carbon, boom, boom, boom. Chlorine attached to the 3rd carbon coming this way? Yeah. 2 types of stereoisomers, enantiomers, diastereomers. Which one's the enantiomer? Let's call this Roman numeral 1. Which one's the enantiomer of this? When you look in the mirror, what happens?
So 3.
I got my right leg up, you got your left. I got my left hand out, you got your... When you look in the mirror, everything switches, right? Go home tonight, do that, and see, make sure your mirror image has everything opposite. You can hold up 2 different things, you can hold up 20. They're all going to be switched in the mirror. What's the enantiomer of RR? SS. These are enantiomers. Don't these look like mirror images? Not really. They're not drawn as mirror images. But guess what? When RR looks in the mirror, what does it see? SS. We'll draw these better so we can see them mirroring each other. We'll draw them as Fisher projections. So, what's the relationship between 1 and 2? Are those mirror images?
No.
If RR looks in the mirror, will it see RS?
No.
Unless it's wrong with the mirror. So it's a stereoisomer, but it's not a mirror image. So what is it? Diastereomers. What does the flow chart say about diastereomers? What does it say? Not mirror images? Stereoisomers that are not mirror images are called diastereomers. There they are. Those are diastereomers. Stereoisomers that are not mirror images. RS is not the mirror image of RR. Diastereomers is a default category. We're introducing them here. Enantiomers, we've already said, have the same identical properties like boiling point, melting point, density, polarity. The only difference is one rotates PP light one way, one rotates the other way. They're mirror images. You expect them to have very similar properties, and indeed identical. These are not. Diastereomers have totally different properties. I mean, they have the same connectivity, but it's like a person with two arms are like this, and then a person with the other arm there is always like this. I mean, that person just can't do what this person can do. All right? I mean, diastereomers have totally different properties. And indeed, in the bromination lab, the two choices were diastereomers. There wasn't there a huge melting point between your two choices? One was like 200 something, the other one was only 100 something. See, diastereomers have very different properties. What's the relationship between the others? Let's see. What's the enantiomer of number 4? If SR looks in the mirror, what does it see? RS. Those are enantiomers. What else we got here? What's the relationship between 2 and 3? Let's put a D there. How about 3 and 4? Diastereomers. Can we call 1 and 3 a DL pair? Can we call 1 and 3 a DL pair?
Because the D and L.
I'm sorry, did I do something wrong? Just because if it's a DL pair, 1 is D and 1 is L. Do you agree that 1 is D and 1 is L?
Yeah.
They're enantiomers. 1 is D and 1 is L. A pair of enantiomers is often called a DL pair. I mean, you have to do the experiment to determine which is which. But see, that's a DL pair. Okay? I'm just telling you the terminology here. And then what?
2 and 4.
Yeah, 2 and 4 was a DL pair. Now the rotation for 1 and 3 is some number, and the rotation for the other is some other number. I mean, the two DL pairs have probably totally different rotations. So 1 is plus, 1's minus. Also, this compound here, in terms of terminology, is either D or L. Okay? R and S is for individual sites, carbons. D and L is the molecule as a whole. Thus we have, this is a DL pair, et cetera, et cetera. to, here it is over here. The compound below. Let's repeat it with the compound below. Oh, yeah. Oh, good. So we need to draw these in Fisher projections. Very good. Yeah, certainly. Thank you. Let's draw one in a Fisher projection. We have two chiral carbons. I'm going to put two crosshairs. The carbon backbone, let's get rid of that. 1, 2, 3, 4. That's actually not right in terms of nomenclature because chlorine comes before hydroxy. But I'm going to number these like that. Your carbon backbone like that usually is straight up and down. So that's like 1, 2, 3, and 4. And it's carbons 2 and 3 that are chiral that we need to show with the crosshairs. It's a double crosshair like this. Okay. I'm going to put methyls here. Those are methyls on the ends. In the Fisher, is that methyl going away or coming towards us? Going away. Up and down means away. I want to look at this with the methyl going away. So do I want to stay on this side of this carbon or on that side of the carbon? I want to stand over here like this and look through here. If I look through here, from that carbon, the methyl's going away from me. The methyl going away, which side is the OH on? Well, it's bold, so it's coming off the board. So if I'm looking through here, it's coming off the board, it's on my... So the methyl going away, the OH is on the left. The methyl going away, the OH is on the left. Now this methyl is going away. So I want to look at carbon 3 with the methyl going away. So I actually want to now stand over here. I have to remember where the ground is. The ground is down here. Carbon 4 is closer to the ground. I stand over here, that methyl is going away. With that methyl going away, is the chlorine on my right or left? It's coming out towards you guys. The methyl going away, the chlorine is on my right. The chlorine is here. What's going back on carbon 3? Or to my left, because if it's going behind the board and I'm looking this way, that's to my left. H. You want to draw in your H's in the Fisher projection. Also H on carbon 2. With the methyl going away from carbon 2, the H is going behind the board, so it's on my right. This is the compound in the Fisher projection. Any particular questions about that? Now, let me get rid of this up here so we have space. Now let's draw the others. Now the others I'm actually going to cheat. And then we'll do some more from scratch on the next example. I'll show you just a quick way. Let's do number 2. Methyl, methyl. That's 1, 2, 3, 4. Where's the OH at? Well, that's the same as this one over here. So it's here and here. What's changed? Chlorine. Chlorine's now over here. Chlorine's here, the H is there. Okay, since we did this one, we can now just draw the others by just doing a little adjustment. Now do it from scratch. I'm not going to look at this one, it's the same as here. But let's look down here. Here's the methyl. It's going away from me. For it to go away from me, I need to be standing down here. It's going away from this carbon. With it going away, is the chlorine on my right or left? Well, it's going behind the wall, that's what the dash means. So if I'm standing here and something's going behind the wall, it's on my left. That's why I drew it on the left. But see, it's switched from this guy because here with the methyl going away, the chlorine's on the right. Okay? Now this is SS. This is going to look like what?
The opposite of the first one.
Exactly opposite. It's going to be here, H here, OH here, chlorine here, H here, and methyl down. That's number 3. What do we know about 1 and 3? Aren't they enantiomers? Do they look like mirror images now? Does 1 and 3, if 1 looks in the mirror, would it see that? Hopefully you can see the mirroring better now. This guy over here. I'll do it real quick from scratch. What's the top methyl? 1, and this is 4, the ground's here. With methyl 1 going away, the OH is on my... Correct. That means the H is there. With this methyl going away, I got to move over here. With that methyl going away, the chlorine is on my right. There's that one. It should look like a mirror of 2. Does 2 and 4 look like mirrors? Yes. Yeah. Both H's on this side, both H's on 2 and 4 hopefully look like mirrors. You can see mirror images easier. Also, you can see planes of symmetry. Look at this. Is there a plane of symmetry here? Actually, the planes there's no trick. You don't have to consider much. Because both of these are coming forward. If we were to draw a plane through here, methyl forward would mirror methyl forward. But is that really a plane? No, because OH is not mirroring OH, obviously. So that's not a plane. Basically, in your fissures, you have either a cross plane, or is that a plane of symmetry? No, 2 H's are not mirroring 2 H's. There's no plane of symmetry. That means the compound's chiral, and thus the mirror image is different. Here's the mirror image, it's different. It's the enantiomer. None of these have planes of symmetry. These are all 4 different compounds. In the next example, we'll see a meso. I'm going to erase. We're going to do the next example. We'll sort of do the same thing fresh again. The next compound has both OHs. How many chiral carbons in the next compound? 2. That's chiral, and that's chiral. How many stereoisomers possible?
Well, technically it's 4, but there's a thing.
Two to the end would be 4. 4 would be, say, the max. But is it really 4? Or are some of those actually going to be the same? Let's draw them in perspective drawings. The first one before, I think both were bolded. Is that right? We can keep it consistent. Were they both bolded before?
Yeah. The second back.
This was bolded. Dash. What was this one? Dashed and bolded. Is that really 4 different compounds? Let's see. R and S should be the same as the previous set because changing this from chlorine to OH is not going to change the priority comparatively. In the previous set, this was what? RR? Yep. And so this was RS. This was what? SS. This was, yeah, it should still be the same. We didn't change priority in switching to OH. What's the relationship between RR? Where's the enantiomer of this?
3.
Enantiomer. Or is it?
Same compound.
Are those really enantiomers?
No, the same.
So they're the same. Why would they be the same?
Fisher projection.
They're the same if the compound has a what? These are the same because why? Because this has a plane of symmetry. Has a plane of symmetry, the mirror image is going to be the same thing. So you're saying that this has a plane of symmetry. And thus the mirror image is the same.
2 and 4 have.
The other that one.
Does this have a plane of symmetry?
No.
It's easier to see planes if we do it in Fisher. Let's draw this in a Fisher projection. I'm going to call this 1 and that 4. And I'm going to draw 1 at the top, 4 at the bottom. These are methyls. I'm not going to do it here. With the 1 methyl going away, the OH is on my... I've got to come over here. Because over here, the methyl is going away. With it going away, the OH, which is coming off the board, is to my... The methyl going away, the OH is on the left. That means the H that's going back is on the right. With methyl 4 going away, I need to come over here. With methyl 4 going away, and that's projected off the board, so I see the methyl going away, and I see the OH on my right. Well, I'm going to put the methyls there. It's just left naked without. Okay? There's that in the Fisher. Do you see a plane of symmetry?
No.
Can I draw right through there? Remember, in the Fisher, you either have a horizontal possible or a vertical possible. Is that a mirror plane?
No.
Oh, OH is not mirroring OH. That's not a mirror plane. Is that a mirror plane? No. OH is not mirroring OH. There's no mirror plane. That means the... Is this the mirror image? Everything has a mirror image. Yes, it's a mirror image because when RR looks in the mirror, it sees an SS. Is this different? We just said there's no mirror plane, so is the mirror image different? Yeah. The mirror image is only the same if it has a plane of symmetry. Now, to really see this, you make models and you see, okay, do they really stack on each other? And they will not. They're like two hands. They will not stack on each other. So let's do the other one. Let's do this one. Methyl 1, methyl 4. We're going to call that methyl 1, that methyl 4. With methyl 1 going away, the OH is on my coming out towards you. Methyl is going away. It's on the left. Look here. Here's the zigzag, 3-carbon zigzag. OH is coming forward. There it is. All right? I'm right here. With that methyl going away from me, I want to draw what I see on the board. I want to draw the OH on the left. See, this is what I'm drawing on the board. It's over here. Right? Methyl going OH is over here. It's right there. Here it's coming forward, but I'm looking through here. Okay? With methyl 4 going away, how is that OH? Methyl 4 going away, it's not coming out to my right, it's going behind the board. That's what the dash means, so it's on my left. There's an H there, H there. There it is. What do you see in that compound? Symmetry. There's your plane of symmetry, which you can see from the fissure. The power of the fissure. This has a plane of symmetry. Where's the mirror image of this? Is that the same compound or different? Same. That's the same compound over there. So these two, is this a DL pair? No. This is only one compound. What do you want to call this compound? That's a meso compound. The mirror image is the same thing. The time we have left, let me make a model of this one. Let me extend it here. Use just a green. Zigzag, like this. Is that it? Black is on the zigzag board. This has OH going forward. That carbon has OH going back. Is that right? Okay. Let me build the one on the end, which we've already said it's the same thing, but let's prove it. Hold on, guys. That's gray. Green. In the plane. No, that's not it.
Your two blacks are down. Turn one of your blacks down. Yeah, your blacks.
Yeah, switch this. That was one of the others, 2 or 4. We're doing this.
Oh my God. There we go.
Is that it?
Yeah.
Okay. Are these mirror images? If that looks in the mirror, will it see that? Yeah.
Yes. Yeah.
Are they the same or different?
Same.
Now look, I can just stack them on top of each other. It's the same compound. It's achiral. What we have here is a compound that has 2 chiral centers. Yes. But the mirror image is the same thing because it actually still has a plane symmetry. A compound that has chiral centers yet is achiral as a whole is known as meso. It's not optically active. It's not chiral. So this is the same compound. So how many total on the board here? There's only 3. You got this one, and that one. That's just a repeat of this. Just like the mirror image of the cliff is the same as the mirror image. That's called meso. What do we call these two? A DL pair. Because those two are chiral. One is D and one is L. Because these two, we showed that there's no mirror image. I mean, there's no plane symmetry. Okay, guys, I know what you're waiting on.